So today I'm gonna do something different. I'm gonna learn Solidity by playing this game, CryptoZombies. And I think after I play this game, I'm probably gonna start the build space stuff. I'm not sure if it's possible to start the build space because from what I remember, they did in classes, the programs they have. So it might be closed for now. I'm not sure how it works, but I'll look into it later. And this I already read. It's pretty much a description of an introduction, but as far as I know, there isn't anything about Solidity here. Just telling you to change these values and experiment with how the thing is gonna look. So play with the sliders, experiment, okay, enough playing around, and then the next one it starts. Starting with the absolute basics. Solidity's code is encapsulated in contracts. So as far as I know, I studied a lot, not a lot, but a little bit about Solidity so far and the blockchain. And it seems to me that a contract is pretty much the same way that a class works in standard programming. And then there are a few differences. Solidity is statically typed. So that means that it's kind of like C++ in the way that you initialize variables. You have to specify the type of the variables. And it's different from JavaScript or Python that's not is dynamically typed, which means you don't have to specify the variables, the type of the variables. And there are also differences in the way that you are incentivized to create variables and functions. No, just variables, because if you create global variables, then you spend more money paying gas when you're going to deploy the contracts. And local variables spend less money because it's a different type of memory allocation. So you're usually more incentivized to create variables inside the function. And I also learned that there are different types of functions, and I still don't know the difference really well, but it seems like one type you can change variables, that global variables inside of the function, and another type you can't change the variables. And you also have to specify the return value, and there is a little bit of differences. But it seems like it's very similar to C++ and JavaScript. Solidity's code is encapsulated in contracts. A contract is the fundamental building blocks of a Ethereum application. All variables and functions belong to a contract, and this will be the starting point of all your projects. Oh, let me start the timer here. I'm gonna put 2 hours, but I might spend more time today. All variables and functions belong to a contract, and this will be the starting point of all your projects. An empty contract named Hello World will look like this. Version pragma. All Solidity source code should start with a version pragma, a declaration of the version of the Solidity compiler this code should use. Yeah, so it works like C++, where you have to compile the code and then run it. It's not run by an interpreter. This is to prevent issues with future compiler versions potentially introducing changes that would break your code. For the scope of this tutorial, we want to be able to compile our smart contracts with any compiler version in the range of 0.5 to 0.6. It looks like this. Pragma Solidity. So I have to do this stuff. And this specifies the version of the contract, which I think this is the standard way to specify versions, even in other programming languages. I remember I wrote this down as a note. It might be somewhere here, where what each number means, but I think this is for the version. When this number changes, then you can't have compatible stuff before, but when these two number changes, you can. Something like that. Don't remember really well. Let me see if I still have here. Maybe it's on C++ info. I remember I took a picture. Package standard here, I think. Yeah, so follows this. The major version should increment when you make incompatible API changes. The minor version should increment when you add functionality in a backwards compatible manner. The patch version should increment when you make backwards compatible bug fixes. This means that patches are bug fixes and minors add new features, but neither of them break what worked before. A major breaks what worked before. And you can also use an oracle, and an oracle is pretty much a bridge between the blockchain and the normal data structures. So I think the most famous ones is probably Chainlink, and then you can make API calls to see, but I'm not really sure about it. So far as I understand, that's how it works. Declaration of the version of the Solidity compiler. This prevents issues with future compiler versions potentially introducing changes that would break your code. For the scope of this tutorial, we want to be able to compile match contracts. Putting it together is a bare bones starting contract. The first thing you write every time you start a new project. Yes. So it's probably asking me to do this. So far, I found that the most annoying thing to understand is the difference between different functions and how you should write them. And there's also Struct, which stands for structure, I think, which is another data type that I'm not very familiar with. And I think to create objects, you use map, which is probably the same way that C++ works from the challenges I was doing, which is a little bit more confusing than just using normal objects. And I also learned that you can pass mapping as an argument into functions. Put it to the task to start creating your zombie army. Let's create a base contract called Zombie Factory. In the box to the right, make it so our contract uses Solidity version. Oh, so I have to put this probably. Maybe. So it specifies that it's between these versions. Create an empty contract called Zombie Factory. So factory. When you're finished, click check answer below. If you get stuck, you can click on. So probably did this wrong. Maybe if I do it like this. Oh, I didn't want to see the answer. I can't try again, apparently. Let's see if I reload. Oh, that's a shame. I think you can only try one time. Oh, but I'm writing how it's written there. Oh, maybe I forgot the semicolon. That might be the problem. And I think contracts have to start with camel case. Oh, if I change something, so oh no, so it's failing, but it's working. Huh. So why is this not working? Contract. I don't understand. I don't think this semicolon at the end of the contract is necessary. I think I'm just gonna look at the answer. I don't get what's wrong here. Maybe I have to put it right beside it. Doesn't work. Maybe like this. I'm just gonna look. Yeah, so I did this. Oh, I wrote contract. Oh, it's the same thing. What's going on? I don't understand. So I have to put another one? Am I crazy or what's going on? Or maybe I have to erase this? That's the problem? Oh, there we go. It's the comments were the problem. Have triumphed, Solidity covers in front of. So now I can move on, I think. Oh yeah, this is the next one. State variables and integers. Great job. Now that we've got shell for our contract, let's learn about Solidity. Deals with variables. Permanently stored in contract storage. This means they're written in the Ethereum blockchain. Think of them like writing to a database. These will be stored permanently in the blockchain. In this example contract, we created uint called my unsigned integer and set it equal to 100. Unsigned integers, push the task or zombie is going to be determined by a 16-digit number. So it has to be long, maybe uint long. 16 digits. Yeah, I'm not really sure how many bytes is 16 digits. The uint data type is an unsigned integer, meaning its value must be non-negative. There's also an int data type for signed integers. Note, in Solidity, uint is actually analyzed for uint 256, a 256-bit unsigned integer. You can declare uints with less bits, uint 8, uint 16, uint 32. Also, it's probably uint 16 that they want me to write. But in general, you want to simply use uint, except in specific cases, which we'll talk about in later lessons. Declare uint named DNA digits equals 16. The conversion between digits and bytes is always confusing for me, even though I studied it a lot already. I still don't remember really well. Maybe I should create this account here. I don't know if it makes any difference. I'm just gonna create a random password. Okay. Math in Solidity is pretty straightforward. The following operations are the same as in most programming languages. Another thing that I struggle with is understanding how to use big numbers, which is also something I've seen people talk about, where you have specific libraries, especially, I don't know in Solidity, but in Node.js, where you can use them to get big numbers because they're important in transactions, because usually the coins vary a lot in the decimals. But it's still very confusing to me to think about it in memory, how big numbers get stored if they don't fit any type, any data type. Math in Solidity is pretty straightforward. The following operations are the same as in most programming languages: addition, subtraction, multiplication. Solidity also supports exponential operator to the power of. Okay. Put it to the task. To make sure our zombie's DNA is only 16 characters, let's make another uint. So uint equal to 10 to the 16. That way we can later use the modulus operator to shorten an integer to 16 digits. And DNA modules and down to the power of 16. Now, so this is the really easy stuff so far. Oh. So uint DNA modulus and set it equal to 10 to the power of the DNA digits. Sometimes you need a more complex data type. For this, Solidity provides structs. Structs allow you to create more complicated data types that have multiple properties. So I guess struct is kind of like maybe an object, or yeah. Note that we just introduced a new type, string. Strings are used for arbitrary length, UTF-8 data. Put it to the task. In our app, we are going to want to create some zombies. And zombies will have multiple properties, so this is a perfect use case for a struct. Create a struct named zombie. Yeah, so like I said before, there's a difference between creating these variables outside of the scope of a function and creating them inside of a function, which is some of the tricky things about this. Create a struct named zombie, or zombie struct to have true properties, a name, a string, and DNA range. Name, string. It's probably zombie. Difference. So still wrong here. Maybe just the order that I put them. Yeah, there we go. I guess order might make a difference. When you want a collection of something, you can use an array. There are two types of arrays in Solidity: fixed arrays and dynamic arrays. Array with a fixed length of 2 elements. Array fixed length contain 5 strings. A dynamic array has no fixed size, can keep growing. You can also create an array of structs using the previous chapter's person struct. Dynamic array, we can keep adding to it. So I guess struct might be like an object. Remember that state variables are stored permanently in the blockchain, so creating a dynamic array of structs like this can be useful for storing structured data in your contract, kind of like a database. Public arrays. You can declare an array as public, and Solidity will automatically create a getter method for it. The syntax looks like this. Person, public, people. Other contracts would then be able to read from but not write to this array. So this is a useful pattern for storing public data in your contract. Put it to the task. We're going to want to store an army of zombies in our app, and we're going to want to show off all our zombies to other apps. So we want it to be public. Create a public array of zombie structs and name it zombies. So I already have this struct there. Yeah, it comes after. So like this. Zombies. So it doesn't say if it's fixed or not. Oh, it has to be public as well. So public zombies. A function declaration in Solidity looks like the following. So the function, the arguments, public. This is a function named eathamburgers that takes two parameters, a string int, a uint. For now, the body of the function is empty. Note that we're specifying the function visibility as public. We're also providing instructions about where the name variable should be stored in memory. This is required for all reference types such as arrays, structs, mapping, and strings. What is a reference type, you ask? Well, there are two ways in which you can pass an argument to a Solidity function. By value, which means that the Solidity compiler creates a new copy of the parameter's value and passes it to your function. This allows your function to modify the value without worrying that the value of the initial parameter gets changed. By reference, which means that your function is called with a reference to the original variable. Thus, if your function changes the value of the variable it receives, the value of the original variable gets changed. Note, it's conventional but not required to start function parameter variables names with an underscore in order to differentiate from global variables. So it's kind of like Python. That way. There's also something called Modifier that I saw, which seems to me that it works exactly in the same way that decorators work in Python. And so this memory is kind of like the ampersand, this sign here on C++, I guess, where you create the reference for the variable outside of the function. I guess that's what the memory does, probably, from what I understand here. So this is required for arrays, structs, mapping, and strings. This allows your function to modify the value of a turing that value. Note is convention but not required to start function parameter variables, names, with an underscore. You'd call this function like so. So just like a normal function. Put it to the test. In our app, we're going to need to be able to create some zombies. Let's create a function for that. So function create zombie. Then there's arguments, public. You should take two parameters, name and string. So string. It has to be memory. Name. And a DNA uint. Don't forget to pass the first argument by value by using the memory keyword. Leave the body empty for now. We'll fit in later. I wonder if this memory thing is gonna affect the way you do things, because you're always gonna have to change the value of the variable outside of the function every time you call the function. So I wonder if that changes anything. Remember our person struct in the previous example. Now we're going to learn how to create new persons and add them to our people array. Also, struct might be like more like a class than like an object. You can also combine these together and do them in one line of code to keep things clean. So use person, then Satoshi equal person. People.push Satoshi. And people is the original array with person. Note that array.push adds something to the end of the array, so the elements are in the order we added them. See the following examples. Put it to the test. Let's make our create zombie function do something. Fill in the function body so it creates a new zombie. Yeah, so now it starts getting more difficult. So zombie is a struct, so I have to do zombie. And adds it to the zombies array. The name and DNA for the new zombie should come from the function arguments. But it doesn't specify which name I'm gonna name the zombie. But I guess it would be like this. Then zombie name DNA. And then I probably have to push. Let's do it in one line of code. Keeps things clean. So might be the name. So zombie I think is correct. And that's the thing here. I'm overloading, I think. Because it's the same name here. But I did it in the way that they told me to do, so I think that's probably what I need to do. Oh, actually, no, the array of zombies actually is zombies. So not overloading. It's just this is creating the array that has the data type zombies. And his name zombies. Has the data type zombie and his name zombies. So creates a new zombie and adds it to the zombies array. Oh, adds to the zombies array. So zombies dot push zombie. So maybe I just need to do this instead and then push. Oh, or maybe push inside of here, like it's showing here. But if it doesn't have a name, how is it gonna know? Oh, is it gonna be? Yeah, I actually don't understand this. Because if you're not putting this into a variable, how is it possible that you're gonna know which one is it? Let's try. Yeah, I'm still doing something wrong here. Yeah, so the problem has to be on this line. Oh, zombie. No. Zombies. Push zombie. Score name. Maybe I have to specify here. But I don't think that's the problem. Note that array.push adds something to the end of the array, so the elements are in order. We added them. Let's make our create zombie function do something. Fill in the function body so it creates a new zombie and adds it to the zombies array. The name and the DNA for the new zombie should come from the function arguments. So I don't see what I'm doing wrong here. Oh, I forgot the semicolon. That's probably what's wrong. Yeah, there we go. Always the semicolon. Private public functions. Solidity functions are public by default. This means anyone. I still don't understand really well how is it possible to create it without making it equal to a variable or something. It just doesn't make a lot of sense to me. Because how are we gonna call it? Maybe just use zombie to call it. And then the difference comes in the name. But in Solidity, functions are public by default. This means anyone or any other contract can call your contract's function and execute its code. Obviously, this isn't always desirable and can make your contract vulnerable to attacks. Thus, it's good practice to make your functions private by default, and then only make public the functions you want to expose to the world. Let's look at how to declare a private function. This means only other functions within our contract will be able to call this function and add to the numbers array. As you can see, we use the keyword private after the function name, and with function parameters, it's convention to start private functions names with an underscore. Put it to the task. Our contract's create zombie function is currently public by default. This means anyone could call it and create a new zombie in our contract. Let's make it private. What if I create a zombie? So just change from public to private. I guess it's similar to C++. So I probably forgot something here. What if I create zombie so it's private function? Don't forget the naming convention. Oh, I need to start with an underscore when it's private. There we go. So this underscore is convention, is required. Or maybe it's just convention and the task that is requiring that. But you probably don't need to put it. It's just convention to put it, so it's probably better to put it. But in this chapter, we're going to learn about function return values and function modifiers. To return a value from a function, the declaration looks like this. So you just say returns and have to specify the return value, which is similar to C++, but it comes after the function declaration instead of before. And you need to put returns, the keyword as well. Function modifiers. The above function doesn't actually change state in Solidity, e.g. it doesn't change any values or write anything. So in this case, we could declare it as a view function, meaning it's only viewing the data but not modifying it. So that's the part that is a little bit confusing. Solidity also contains pure functions, which means you're not even accessing any data in the app. Consider the following. This function doesn't even read from the state of the app. It returns value depends only on its function parameters. So in this case, we would declare the function as pure. So when you're not accessing anything outside of the function scope, is probably pure. But what is function doesn't actually change state. So when a function doesn't change state, is view. And when it doesn't change state and doesn't access variables outside of the scope, then it's pure. So this is view because it's accessing greetings, which is outside of the scope. And this is pure because it doesn't access anything outside of the scope. This function doesn't even read from the state of the app. Its return value depends only on its function parameters. Note it may be hard to remember when to mark functions as pure or view. Luckily, the Solidity compiler is good about issuing warnings to let you know when you should use one of these modifiers. The other thing that I'm not sure about is what IDE you should use to deploy contracts. So far, I've seen Remix seems to be the one used. But I know you can use any IDE to build the contract, but how to deploy it is a different story. And I think Remix has some things to deploy contracts, but I'm not really sure. That's also something I'm probably gonna look at later. Put it to the task. We're going to want a helper function that generates a random DNA number from a string. So I'm gonna write another function. Create a private function called function generates random DNA. So string memory string and returns uint. Oh, so you can have functions that return. I guess the data type is gonna be the data type of the function is gonna be equal to the return, but it doesn't necessarily mean that the arguments have to be. So yeah, it works pretty much like C++, I think. Returns are uint, so I think, yeah, I have to do private returns uint. And then I have to specify if it's view or not as well. And the view or pure comes before returns. Don't forget to set the data allocation of the string parameter to memory. This function will view some of contract's variables but not modify them. So view. The function body should be empty at this point. So what did I miss here? Generate random DNA seems fine. String memory string. Private view returns uint. Oh, I have to put this on parentheses. There we go. We want our generate random DNA function to return a semi-random uint. How can we accomplish this? Ethereum has the Ethereum is the blockchain is deterministic, so you can't. I think you can, but it's really hard to have true random numbers. There are some workarounds, I think, for that, but I'm not really sure. Ethereum has the hash function CAC 256 built in, which is a version of SHA-3. Hash function basically maps an input into a random 256-bit hexadecimal number. A slight change in the input will cause a large change in the hash. It's also useful for many purposes in Ethereum, but for right now, we are just going to use it for pseudo-random number generation. Also important, CAC 256 expects a single parameter of type bytes. This means that we have to pack any parameters before calling CAC 256. As you can see, the return values are totally different despite only one character change in the input. Note, secure random number generation in blockchain is a very difficult problem. Our method here is insecure, but since security isn't top priority for our zombie DNA, it will be good enough for our purposes. Typecasting. Sometimes you need to convert between data types. Take the following example. Because A turns not 8. We have to typecast B as a uint A to make it work. The above, A times B returns a uint, but we are trying to score it as a uint 8, which could cause potential problems. By casting it as a uint 8, it works, and the compiler won't throw an error. Put it to the task. Let's fill in the body of our generate random DNA function. Here's what it should do. The first line of code should take the cacac, whatever this is. And apparently you don't need to import. I don't think libraries exist. Maybe they do. In Solidity. Yeah. I haven't seen anything talking about libraries, I think, yet. And I'm not sure if that's even possible. But I guess we'll see later on. And this takes ABI dot encode packets and then the name of the argument, which is gonna generate a random number based on the hash function, which is gonna be different each time. I think that's what this is doing. First line of code should generate episode of random hexadecimal, typecast it as a uint. And I have to make it equal to something, I guess. No, I have to make something equal to this. And finally start the result in a unit called rand. We want our DNA to only be 16 digits long. Remember our DNA modules. So the second line of code should return the above value modules. So it should return rands modules, DNA modules, I think. Which is this variable here, which is a 16 digits. So I'm just gonna take some time to think about it, see if I understand what's happening. So I have this function here, which is private, returns uint. It's creating a random number, and it is accessing this variable. That's why it's view on the return. And it's gonna return the remainder of this random hash divided by 16. But is this even possible? Because this is not a number. Just realize that now. So maybe I'm doing something wrong. Yeah, I'm probably doing something wrong. I'm casting it as an uint, but this is supposed to be this thing here, which is not necessarily a number. Encode packet. Also, I have to convert this inside here to uint probably. because of this typecasting thing here. And I guess that will generate a pure random number instead of this string here. Sometimes you need to convert between data types. Take the following example. So I have two different types, typecast. So I guess when you do this, it converts between types. In the above, it turns uint, but it could cause potential problems by casting it as uint8. Works. Let's fill in the body of our generate random function. First line of code should take this hash of ABI encode packet string. Also maybe, well, so DNA is uint, this is uint. So I think the casting should come here. But here it says that I should create this encode packet to generate on random hexadecimal. Typecast it as a uint. Also, maybe I have to do this outside actually. The whole thing. Yeah, that's probably what I have to do. That makes more sense. Because you have the hash, then you convert it. I thought because I was initializing as uint, maybe the conversion is different, but I guess you have to convert after. Yeah, there we go. We're close to being done with our random zombie generator. Let's create a public function that ties everything together. We're going to create a public function that takes an input, the zombie's name, and uses the name to create a zombie with random DNA. Put it to the task. Create a public function named create zombie. So function create zombie, create random zombie. Random zombie. It will take string, memory, name, and DNA. Probably. Oh. One parameter named name. A string of data. Note, declare this function public. So public. And it's gonna access the values. So it's probably view. I think I kind of forgot what the pure means. Well, pure is when you... Yeah, pure is when you don't have access to anything outside of the function scope. View is when you have access but you don't modify the values. So it might be just normal. Declare this function public just as you declare previous functions private. The first line of the function should run the generate random function on name and start in a uint named rand DNA. Second line should run the create zombie function and pass its name and rand DNA. The solution should be 4 lines of code including the closing of the function. So I think it's not neither view or pure, because I'm using this string memory name, but I'm not really sure about that. So it returns, what is it going to return? First line of the function should run the generates random DNA function on name. And store it in a uint named, I think I can put it as view. Uint named, so I'm gonna write this down. It's gonna be the function generate random DNA passing name, which is this function here, and it's gonna create the random random number. And start and you need run DNA. The second line should run the create zombie function and pass it name and run DNA. So I guess you just declare like this. Passing name and rent DNA. The solution should be far line of codes. 4 lines of code. So I have 3 now. So I'm missing 1. So maybe I should create a variable. Oh, I need to return, I think. Or maybe not. Because when I'm calling this, it's already creating the zombie. Using this function and pushing to the array of zombies. So I'm generating random DNA and create zombie. Oh, I think the overall function should be 4 lines maybe. So this is probably not view. Well, it doesn't return anything. So maybe I can erase this. Yeah. There we go. So I guess I'm not really accessing anything outside. I'm just calling the functions. So it would have to be view if I was accessing a variable. Yeah, but since I'm not, because the variables are being accessed through the other functions. I think that's why. Our contract is almost finished. Now let's add an event. Yeah, so I guess here it creates a different variable and then, but it's not directly accessing anything outside of the function. And that's why I don't have to specify there. That is view. If it was accessing these things directly, then it would be view, I think. I'm just thinking about the way that they decided to do this. If there is a pattern here or logic for the way people usually create these things. Because obviously they could put everything in one function, I think, if they wanted. But yeah, it makes sense to separate them in different ones because then each one does a certain specific thing. And I guess it's probably also common practice to put these things inside of functions, so you use less things outside of the functions. And that should be the best design, probably. To create as many functions as possible and use the other functions inside of other functions instead of accessing things directly. Events are a way for your contract to communicate that something happened on the blockchain to your app front end, which can be listening for certain events and take action when they happen. Event integers added. Function and public returns. Fire an event to let the app know the function was called. Your app front end could then listen for the event. A JavaScript implementation will look something like your contract.integers added function error result. So it's kind of like a promise in JavaScript where you do a call and then you do some try catch or then catch to get the response. And this is probably the same as creating an API at post, or I'm not sure if it's post or get. Probably post because you're making it available for the client to get. So it's a get and the client, but it's post for the back. To let the app know the function is called. So this is the creation of the event, and this is when it's gonna be emitted. Put it to the test. We want an event to let our front end know every time a new zombie was created, so the app can display it. Declare an event called new zombie. It should pass zombie ID. So event new zombie. It should pass zombie ID. Now I think I have to put memory. String memory name. And maybe not because it's outside of the. It's outside, yeah. It's probably just string name because I'm not passing it as an argument to a function, and it's outside of the. It's on the global scope of the contract. Name is string, and DNA IU and modify the create zombie function to fire the new zombie. So create. So this will be meet, then new zombie and pass. But where is the ID? It should pass zombie. Well, modify create zombie function to fire new zombie event. So I guess this is correct. New zombie, new zombie. After adding the new zombie to our zombies array, you're going to need the zombies id.array.push returns a uint of the new length of the array. I don't understand this part. And since the first item in an array has index 0, array.push, -1 will be the index for the index of the zombie also. It's gonna be in a uint called ID. Zombies.push -1. It's a little bit confusing. The second one is obviously name and DNA. Index of zombie. Store the result of zombies.push -1. Yeah, I don't understand how this works really well. Because you're pushing something. I guess when you do this, it returns the last index. That's probably why. And then -1 gives the index of the last one. It got added. So you can use this in the new zombie event. Let's see if it works. Also, the problem is here and there. We need to put this thing probably. Yeah. Zombies, uint ID, zombies.push. Yeah, I don't understand what I'm supposed to do. I'm going to need the zombies ID.array.push. Returns a uint of the new length of the array. And since the first item is an array has index 0, array.push -1 will be the index of the zombie we just added. Yeah, so the array is this one. Zombies not push -1. So I don't get it. Uint called ID, which I did. So we can use this in the new zombie event in the next line. So did I forgot something? Semicolon or something? So maybe I have to declare it here and make it -1 here, but I don't know if that makes sense to me. It's probably not the correct way. Oh, there. Yeah, that doesn't make sense to me. Well, I guess, yeah, it was like I was talking about. When you push, the return value of the push method is gonna be the index of the new thing, the index of the last element, and then you do -1 to get the previous one. I guess that's how it works. But you can probably use the index as well to access, I think. Yeah, but then it's more, you probably need to write a loop or something like that. Our Solidity contract is complete. Now we need to write a JavaScript front-end that interacts with the contract. Ethereum has a JavaScript library called web3.js. In a later lesson, we'll go over in depth how to deploy a contract and set up web3.js. But for now, let's just look at some simple code for how web3.js will interact with our deployed contract. Don't worry if this doesn't all make sense yet. Here's how we would access our contract. So we have ABI. ABI stands for Abstracted Binary Interface, I think. And it's pretty much the bridge between the code in Solidity and the machine code in the EVM of Ethereum, which is the virtual machine that runs Ethereum. Or other protocols. Zombie factory contract. This factory thing is also confusing for me still. Var contract address our contract address on Ethereum after deploying. Zombie factory contract that has access to our contract public functions, events. Some sort of event listener to take the next input. So this is all in JavaScript. to interact with the contract. So I guess this is jQuery syntax. And it's creating an event listener. That is click. Which is gonna have a name input. The value of the name input. Yeah, listener should take the text input. Call contracts create a random zombie function. Using zombie factory, which is the address of the contract, then calling the function. Listen for the new zombie event and update the UI. So var event equals the address of the contract dot new zombie, which is the event that was created on the contract. Then run the function if error return, which is the catch, and generate zombie results. Guess the information, I think. Take the zombie DNA and update our image. Function generates zombie ID name DNA. That DNA string. Bad DNA with leading zeros if it's less than 16 characters. So that's so it's standard. So it's always 16. Let's zombie details. First, 2 digits make up the hand. We have 7 possible hands, so divided by 7 to get a number 0 between 0 and 6. Then add 1 to make it 1. 1 through 7. Then we have 7 image files named head 1 through head 7. We load based on this number. Last 6 digits control color, updated using CSS filter. Hue rotated with chest 360 degrees. What our JavaScript then does, it takes the values generated in zombie details above and use some browser-based JavaScript magic. We're using view.js. Just swap out the images and apply CSS filters. You get all the code for this in a later lesson. Give it a try, go ahead. Type in your name to the box on the right. So I guess it's here. So this is kind of like e.event.target. No, yeah, e.target.value for listening to inputs, this function here. For listening to form inputs. And then every time you type, it changes the properties based on the substrings of the input. I guess. I think that's what's happening. Once you have a zombie you're happy with, go ahead and click next chapter below to save your zombie and complete the lesson 1. So I think this one is fine. Congratulations, you have completed lesson 1 of CryptoZombies. You're officially one step closer to building your own games on Ethereum. So I wonder how many lessons this has. Oh, so here. So 2, 3. So there's 6 lessons here. Chain link path, centralized oracles. So there's a lot actually, a lot more than I thought. It's part of the blockchain ecosystem. Yeah, so I'm probably gonna do all of this, I think. There's no reason not to. Yeah, so this is the beginner stuff. Yeah. I assume it's gonna get a lot more complicated later, probably. So you've made it to lesson 2. Impressive if you're better. Skip those. Sorry. The 2 will teach you how to multiply your zombies army by feeding on other life forms. We cover some more advanced Solidity concepts, so it's highly recommended that you complete lesson 1 before starting. In lesson 1, we created a function that takes a name, uses it to generate a random zombie, and adds that zombie to our app's zombie database on the blockchain. Lesson 2, we're going to make our app more game-like. We're going to make it multiplayer and also be adding a more fun way to create zombies instead of just generating them randomly. New zombies by having zombie feed, put it to the task. There's a simple demo of feeding to the right. Click on a human to see what happens when your zombie feeds. I think I just have to click. You can see that the new zombie's DNA determined by your original zombie's DNA as well as the host's DNA. When you're ready, click next chapter to move on. Let's get started. Yes, I guess this is just the introduction. Let's make our game multiplayer by giving the zombies in our database an owner. To do this, we'll... Oh, that's another thing that's kind of confusing. I think these things are like special methods of smart contracts for obvious reasons. To do this, we'll need two new data types, mapping and address. Addresses, the Ethereum blockchain is made up of accounts, which you can think of like bank accounts. An account has a balance of Ether, the currency used on the Ethereum blockchain, and you can send and receive Ether payments to other accounts. Just like your bank account can wire transfer money to other bank accounts. Each account has an address, which you can think of like a bank account number. It's a unique identifier that points to that account, and it looks like this. This address belongs to the CryptoZombies team. If you enjoy CryptoZombies, you can send us some Ether. We'll get into the nitty-gritty of addresses in a later lesson, but for now you only need to understand that an address is owned by a specific user or smart contract. So we can use it as a unique ID for ownership of our zombies. When a user creates new zombies by interacting with our app, we'll set ownership of those zombies to the Ethereum address that called the function. Mappings. So every time someone calls the function, is gonna assign the ownership of the zombie to the address of the person that contracted. Lesson 1, we looked at structs and arrays. Mappings are another way of storing organized data in Solidity. Defining a mapping looks like this. So yeah, understanding the difference between mapping and structs is still not very clear to me. For a foundation app, storing a uint that holds the user's account balance. Mappings, address uint. Account balance. Or could be used to store lookup usernames based on user ID. A mapping is essentially a key value store for storing and looking up data. In the first example, the key is an address and the value is a uint. And in the second example, the key is a uint, the value a string. So I think I'm gonna search to look at this stuff later. What is the difference between struct and mapping Solidity? I also don't know how difficult it is to find things about it because there's probably, but by now I think there's a lot of people already. So there's probably a lot of people that have already answered common questions about. I'm trying to understand about how mapping struct arrays work compared to each other. I don't know currently how exactly structs work, but a little bit more about mappings. It all comes down to the fact that you're using arrays to store these addresses and those arrays grow without bound, and because you're always going to iterate through the full length of arrays, you might end up having to spend immense amount of gas just to look up some given address inside of your array. In order to solve this issue, stop using arrays altogether inside of your contract and instead use a slightly different data structure. The data structure that you should use for storing all these addresses rather than being an array, it will be a mapping. A mapping is a reference type that is available to us inside of Solidity. A mapping is like a collection of key value pairs, so it's similar to JavaScript object. Okay, so it is like I was thinking. There are some discrete and definite differences between a mapping and JavaScript object. So why is a mapping going to solve your problem? It all comes down to the search time for each of these data structures. In the computer science discipline, whenever we are trying to find some piece of data inside an array, the best case we can get for running that search is a linear time. When you say that search inside of the array is a linear time, that means that for every additional record, blah blah blah. The big difference between an array and mapping is that doing a search inside of a mapping is what is called computer science discipline constant time. When you say constant time, so pretty much the difference between struct and mapping is just the structure of the search, from what I understand. So I guess on struct you can't access the values by the keys. You have to access by index, and that takes a longer time because you have to loop through the array. I think that's the difference. And mapping you can use whenever you wanna retrieve specific information based on the keys. But I'm not really sure if struct is always an array. And can you make a struct of a different type? The following tutorial is a part of our 100% course. Struct is a Solidity. Struct in Solidity is just a custom type that you can define. You define the struct with a name and associated properties inside of it. Also, struct is a custom type. Yeah, that makes sense. It's our new file in the remix ID called. Yeah, so mapping is more like an object, and struct is more like creating a type. I think I get it now. Here we have a struct of instructors, which will store their name, first name, last name. It will also be handy if we could reference each instructor by their Ethereum addresses. That's where we will create a mapping. Solidity mapping is referred to a hash table, which consists of key types and value types, type pairs. We define a mapping like any other variable type. So the mapping address to the instructor, which is a type. Here we are creating a mapping which accepts the first key type, in our case we'll address, adding to a mapping. Being that our smart contract structure is now significantly different from the previous contract, let's examine what it takes to add instructor to the new format. Yeah, so I'll probably look into this more after. I think I get it better now than I did, but it's still gonna take me some spaced repetition until I finally integrate the concept and the differences well. So I think I read this stuff. I think I stopped here. Yeah, in lesson 1 we looked at structs and arrays. Mappings are another way of storing organized data in Solidity. Finally, my mapping looks like this. Yeah, so it's pretty much referencing what's gonna be the data type of keys and the data type of values on the initialization. A mapping is essentially a key value store for storing and looking up data. In the first example, the key is an address and the value is a uint. In the second example, put it to the test. To store zombie ownerships, we're going to use two mappings. One that keeps track of the address that owns a zombie, and another that keeps track of how many zombies an owner has. So I'm gonna do mapping. Create a mapping called zombie owner. The key will be a uint. You store and look up the zombie based on its ID and the value and address. The name should be zombie true owner. Create a mapping called owner zombie count. The key is an address. The value uint. Oh, here it has to be lowercase. So this maps the ID to the address, and this maps the address to a number on the zombie count, to the number of zombies that the owner is gonna have. So I did something wrong here. And the value and address. Address uint. Also, I also need to specify that it's public here. So everyone has access to this. So do I have to put public on both? Probably not. There we go. Now that we have our mappings to keep track of who owns the zombie, we will want to update the create zombie method to use them. In order to do this, we need to choose something called message.sender. Message.sender. In Solidity, there are certain global variables that are available to all functions. One of these is message.sender, which refers to the address of the person or smart contract called the current function. So sender is the one that's called. I think I'm gonna write this down. Message.sender refers to address who called current function. Note, in Solidity, function execution always needs to start with an external caller. Our contract will just sit on the blockchain doing nothing until someone calls one of its functions. So there will always be a message.sender. Here's an example of using message.sender and updating a mapping. And the other interesting thing is thinking about how, given that they would just sit there if no one calls, how are they being called? I guess it's through the oracle. But how is the bridge being made? I still don't understand really well that. The connection between the blockchain and the normal databases and websites. I guess it's through those libraries, but I just don't understand how they can interact with the. I think I kind of get it actually, but I'm not really sure if that's really the case. Where you have a bunch of blocks that have a bunch of transactions. Each transaction is methods, it's functions being activated, and those functions are activated based on the calls that are made to them through these oracles. I know that each block, each transaction, each part of each node, I don't know if that's the right way to say it, but the block of transactions, each one has a unique number called nonce. And then the hashing to compute happens from block to block. That's how they are connected. And then each block has a bunch of transactions, but I still don't understand how the transactions are, how they are connected. Here's an example of using message.sender and updating a mapping. So here's the mapping. Update our favorite number mapping to store my number under message.sender. So update our favorite number, which is the mapping, to store. So this is the key with the address of the account that called the contract, the function. And this is the value, which is the number. The syntax for storing data in a mapping is just like with arrays. Retrieve the value stored in the sender's address. It will be 0 if the sender hasn't called setMyNumber yet. In this trivial example, anyone could call setMyNumber and store a uint in our contract, which would be tied to their address. Then when they called what is my number, they would be returned the uint that they stored. Use a message that sender gives you the security of the Ethereum blockchain. The only way someone can modify someone else's data would be to steal the private key associated with their Ethereum address. Put it to the test. Let's update our CreateZombie. So it's here. So CreateZombie is the function that calls the other functions. It creates the ID. And then emits that it created the ID. It creates the ID and simultaneously push the new zombie to the zombie struct, which is the array of zombies. To assign ownership of the zombie to whoever called the function. First, after we get back the new zombie's ID, let's update our zombie to owner mapping to store message.sender. So zombie to owner is going to store message.sender. Probably going to be equal to ID. Under that ID. Second, let's increase owner zombie count for this message.sender. Increase, so it's the other mapping. So I guess it's pretty much the same thing. I just put the address, which is message.sender. Oh, here it has to be the other way around, actually, I think. Because the key is the ID and the address is a message.sender. Owner zombie count. Then here is gonna be the count, but how I'm gonna do it? In Solidity, you can increase a unit with ++ just like in JavaScript. Your final answer for this chapter should be 2 lines of code. Yeah, but how I'm gonna increase the number? If I do just ++, it doesn't make sense. If I create another variable, then it's 3 lines, so it doesn't make sense as well. After we get back the new zombie's ID, let's update our zombie to owner. Mapping to store message.sender under that ID. Which I think is correct. Second, let's increase owner zombie count. For this message.sender. Yeah, but let's check and see. Oh, so maybe I just put like this. But, oh, it works. Yeah, that's kind of a weird way to think about it because, well, I guess I am increasing actually. Because it's the same thing as making it equal and +1. And I think it's the same structure as the array where when I type it like that, I'm actually accessing the value of the uint through the key. While simultaneously creating the mapping. Yeah, that's the part that was confusing, I think, for me. Because you're creating the mapping, the instance of the key value pair on the mapping, and at the same time increasing the value. Which I don't I didn't see, I think. Maybe you can do this on other languages, but I never did it and I never saw anyone doing it. Lesson 1, we made it so users can create new zombies by calling create random zombie and entering our name. However, if users could keep calling this function to create unlimited zombies in their army, the game wouldn't be very fun. Let's make it so each player can only call this function once. That way, new players will call it when they first start the game in order to create the initial zombie in their army. How can I make it to this so this function can only be called once per player? For that, we use require makes it so that the function will throw an error and stop executing if some condition is not true. Compares if name equals Vitalik, throws an error and exits if it's not true. Side note, Solidity doesn't have native string comparison, so we compare their CAC 256 hashes to see if the strings are equal. So it's requiring that this string is equal to the Vitalik, but how would you know? Oh, yeah, how would you know this one? If you call this function with say Vitalik high, it will return high. If you call it with any other, I guess you can use message.sender actually instead of this on this case. Thus, require is quite useful for verifying certain conditions that must be true before running a function. Put it to the task. In our zombie game, we don't want the user to be able to create unlimited zombies in their army by repeatedly calling create random zombie. It would make the game not very fun. Let's use require to make sure this function only gets executed one time per user when they create their first zombie. Put a require statement at the beginning of create random zombie. The function should check to make sure owner zombie count is equal to 0. Yeah, but what if they want? I guess you can make other conditions in case they want more. You can make less than the whatever number you want. So it's checking if owner zombie count message sender, which is this mapping here of the counts of each address, is equal to 0. And if it's not, it's gonna break the function. Throw an error otherwise. Yeah, I guess I don't need to put the error. Maybe I have to wrap around this stuff here. So it doesn't have native string comparison, so we compare their CAC 256 hashes to see if the strings are equal. Also, this is when you're comparing strings, you have to use this. So we use the ABI, the binary interface with the encode packet to get the hashes of the strings. I think I get it now. Note in Solidity, it doesn't matter which term you put first, both orders are equivalent. However, since our answer checker is really basic, it will only accept one answer as correct. It's expecting to come first. Okay. Let's see what time it is. I'm already getting a little bit tired. Still 28 minutes. I guess it's from talking a lot. I think I'm gonna get some water. Be right back. Our game code is getting quite long, where the making one extremely long contracts sometimes makes sense to split your code logic across multiple contracts to organize the code. One feature of Solidity that makes this more manageable is contract inheritance, which is pretty much class inheritance. But I'm thinking, I wonder what's the best thing to do that people usually do, because it might be the case that you just pay more when you're deploying multiple contracts. So to me, it makes more sense to put everything in one contract. Even if it gets extremely big, because you can develop in multiple contracts and then just separate them. But then it might affect the global scope, probably. Yeah, it might affect the global scope and how things are interacting with each other. So that might be the reason why people would do this. So I think you just use the is keyword to inherit. Inherits from dog, yeah. That means if you compile and deploy baby dog, you have access to both catchphrase and another. In the next chapter, we're going to be implementing the functionality for zombies to feed and multiply. Let's put this logic into its own contract that inherits all methods from zombie factory. So make a contract. There's also constructors as well. I mean, contracts just like classes. Zombie feeding, and then here is zombie factory. Should inherit from a zombie. Maybe it's this. Let's see if I put the. Oh, so I can put this. Okay. You notice we just cleaned up the code to the right, and you now have the tabs at the top of your editor. Go ahead, click between them. So one is each one for each contract. Now we've set up multi-file structure. We need to use import to read the contents of other files. Oh yeah, so that makes sense. So I guess you can have libraries as well in Solidity. But how does it work on the blockchain? That's the question. So if we had a file named some other contract as song in the same directory as this contract means. Okay, so import zombie factor song dot song, and the gas should be like this. There we go. There are two locations you can store variables: in storage and in memory. Storage refers to variables stored permanently on the blockchain. Memory variables are temporary and are erased between external function calls to your contract. Think of it like your computer's hard disk versus RAM. Most of the time, you don't need to use these keywords because Solidity handles them by default. State variables declared outside of the functions, are by default stored and written permanently to the blockchain, while variables declared inside functions are memory and will disappear when the function call ends. So yeah, for storage you need to pay gas. That's the thing, because it's stored permanently, and then in the memory you pay less gas because it's less expensive. However, there are times when you do need to use these keywords, namely when dealing with structs and arrays within functions. So, where is it? Seems pretty straightforward, but Solidity will give you a warning telling you that you should explicitly declare storage or memory here. So instead, you should declare it with the storage keyword like sandwich storage. In which case, my sandwich is a pointer to sandwich index in storage. I guess it's because you have to store the thing in the permanent memory. Otherwise, it's gonna be erased from the blockchain after you create. So there might be vulnerabilities there if that was the case. Start as it, and this will permanently change sandwich index on the blockchain. If you just want a copy, you can use memory. Also, you can use both, but you have to specify. In which case, another sandwich will simply be a copy of the data in memory. You just modify the temporary variable and have no effect on sandwich index plus 1. But you can do this if you want to copy the changes back into blockchain storage. Don't worry if you don't fully understand when to use which one yet. Throughout this tutorial, we'll tell you when to use storage and when to use memory. The Solidity compiler will also give you warnings to let you know when you should be using one of these keywords. For now, it's enough to understand that there are cases where you need to explicitly declare storage or memory. Put it to the test. It's time to give our zombies the ability to feed and multiply. When a zombie feeds on some other life form, its DNA will combine with the other life form's DNA to create a new zombie. Create a function called feed and multiply. It will take 2 parameters. Yeah, so now is the time where it starts to get hard because I already forgot this stuff from before. But I think it's like this, then it's gonna be either public or private, and then it's gonna have view returns in the statement, then this. Yeah, this is probably this is the way that you write it, I think. Create a function called feed and multiply. It will take 2 parameters zombie ID. And target DNA. This function should be public. We don't want to let someone else feed their zombies. So first, let's make sure we own the zombies. So it's gonna use required probably. Add a required statement to verify message.sender is equal to this zombies owner, similar to how we did in the create random zombie function. Yeah, so this, I think, yeah, how I'm gonna do this, because I probably have to get the function from here, but I'm not sure if I need to specify like zombie factory dot the function, or maybe I just use the ID. And then if I use the if I'm using message.sender, or maybe message.sender, no, it's the address, so it's gonna be a string, I think. So I have to convert that using the algorithm to make the hash. Again, because our own answer checker This primitive is expressed in mesh first. Normally, when you're coding, you can use whichever order you prefer. We're going to need to get this zombie's DNA. So the next thing our function should do is declare a local zombie named myZombie, which will be a storage pointer. Set this variable to be equal to index zombie ID in our zombies array. Yeah, I have no idea. It's kind of confusing. No, it's starting to get to the point that it becomes confusing. And not so much because of the things, but because of the way that they wrote here. You should have 4 lines of code so far, including the line with the closing. Flesh out this function in the next chapter. So it should be 2 lines of code inside of the function. And I guess it's not going to return anything, so I don't need this. And it's not going to modify anything, so it's probably view is not necessary. The only thing is this require check that I don't know if I should use this stuff or not. Yeah, because here I made it with this. Yeah, so I have the addresses stored in this mapping. So maybe I can use the mapping instead with message.sender. Zombie true owner. But I'm not sure if this is gonna work because this is coming from the other file. I'm not specifying it. And I have to put the ID. So maybe zombie ID. Well, was message.sender equals this. Maybe this. And then I have to put it inside the thing. Okay, so I'm not sure what's going on here. Let me try to put this inside of this thing. This impact thing. Oh, I forgot to do the second line. Maybe that's the problem. We're going to need to get this zombie's DNA. So the next thing our function should do is declare a local zombie named myZombie. So zombie, myZombie, which will be a storage pointer. So set this variable to be equal to index zombie ID in our zombies array. So this is gonna be equal to zombies zombie ID. And it's gonna be storage here, I think. Yeah, storage comes before. Yeah, so this is problem. So I guess it was right the first time I did it. So I guess these are considered as numbers, not strings. Yeah, there we go. But it's weird because usually the addresses have letters as well, so I'm not sure how that works. Maybe it's because of it's a hash. The address itself is a hash function or something like that. So it is considered as a number. But I don't understand that really well. Yeah, because I'm comparing two addresses. And the address type is different than a string type. Yeah, it's probably because the address is kind of like the hash function from the smart contract point of view, and not a string. The string of letters or numbers is just the thing that gets used to get. Yeah, I'm not sure. I'm gonna have to study more about that. I should think about the question that I have. How are addresses computed in the blockchain? I guess that's the question. How the machine code perceives how the EVM perceives the address. I understand that miners have to solve an equation, a hash equation to put blocks. Yeah, but I don't really remember really well how it works and how this have to do with address. I think the questions I have is first, how are addresses generated? That's one, I think. So, is it true or well, maybe it should this here. How are addresses generated and what data type is an address? It's not really that I want to know. Is I want to know how the contracts convert the address. Like what is happening on the backend. But if I search for how they are compiled or something like that, then I might get different answers that I don't want. How are maybe if I search for how the message.sender works, how it is constructed. I'll think about this later, but I'll write down a how message, a sender, yes, understand address. The formula for calculating a new zombie DNA is simple. The average between the feeding zombie's DNA and the target's DNA. Later, we can make our formula more complicated if we want to, like adding some randomness to the new zombie's DNA. For now, we'll keep it simple. We can always come back to it later. Put it to the test. First, we need to make sure that target DNA is longer than 16 digits. To do this, we can set target DNA equal to target DNA, the remainder by DNA modules, to only take the last 16 digits. So it's the same thing that we did in the first contract. Note you can access the properties of myzombie using myzombie.name and myzombie.dna. Once you have the new DNA, let's call. So let me focus on the first one first. That DNA, target DNA. So this one. You can set target DNA equal to. So target DNA. I wonder if I can do this. Probably yes. I had to guess. So I'm gonna try. DNA modules. It's interesting that I don't have to specify as well the other file, the other contract on this one. And I guess it's because it's inheriting, that's why. I forgot about that. So because it inherits already knows all the functions and variables, global variables that exist on the other contract, which are saved on storage in the blockchain. That's why I don't have to specify, probably. Next, our function should declare a uint named new DNA. Uint new DNA. And set it equal to the average of my zombie's DNA and target DNA, as in the example above. So my zombie dot DNA plus target DNA divided by 2. Yeah, my zombie.dna. So it's probably correct. Once I have the new DNA, let's call create zombie. You can look at the zombie factor.sol tab if you forgot which parameters this function needs to call it. Note that it requires a name, so let's set our new zombie's name to no name for now. So it's gonna be string memory no name. Or maybe, yeah, I don't need to pass this actually. It's just gonna be this string. And then the new DNA, probably. Let's see if I got that correctly. Yeah, so name and DNA name comes first. So I guess private functions are only accessible through contracts that inherit them. And then public functions are available for everyone in the blockchain, maybe. I think that's how it works. So create new zombie, no name, new DNA. For you Solidity wizards, you may notice a problem with your code here, for our code here. Don't worry, we'll fix this in the next chapter. Yeah, so this doesn't work. So I have to do it like this. It's still, so maybe it wasn't that, it was a different problem. So target DNA equals target DNA. Oh, I forgot the T here. There we go. I think I'll do this one more and then I'll stop. And I might come back later to try to. I want to finish this fast so I can start doing the build space stuff. But maybe it's not good actually to finish fast. Maybe it's better to space out so I retain more information. The code in our previous lesson has a mistake. If you try compiling it, the compiler will throw an error. The issue is we tried calling the createZombie function from within zombie feeding, but createZombie is a private function inside zombie factory. Oh, so that's the thing that I was talking about, and I wasn't really sure. This means none of the contracts that inherit from zombie factory can access it. Internal and external. In addition to public and private, Solidity has two more types of visibility for functions, internal and external. Internal is the same as private, except that it's also accessible to contracts that inherit from this contract. Here. External is similar to public, except that these functions can only be called outside the contract. They can't be called by other functions inside that contract. We'll talk about why you might want to use external versus public later. For declaring internal or external functions, the syntax is the same as private and public. So I guess I have to erase this and then set up internal. I don't think I need to write private internal, just internal. The syntax is the same as private and public. So I guess C++ also has this where you have protected functions as well as private and public. And I think it might be the same concept here. Change createZombie from private to internal so our other contract can access it. We've already focused, you're back to the proper tab. Yeah, so this was an easy one. Maybe I'll do one more before I stop. It's time to feed our zombies and what do zombies like to treat the most. So serious. In order to do this, you need to read the kitty DNA from the CryptoZombies smart contract. You can do that because the CryptoZombies data is stored only on the blockchain. Isn't the blockchain cool? Don't worry, our game isn't actually going to hurt anyone's CryptoZombies. Only reading the CryptoZombies data, not able to actually delete it. Interacting with other contracts. For our contract to talk to another contract on the blockchain that we don't own, first we need to define an interface. Let's look at a simple example. Say there was a contract on the blockchain that looked like this. This would be a simple contract where anyone could store their lucky number and it will be accessed with their Ethereum address. Then anyone else could look up that person's lucky number using their address. Now let's say we had an external contract that wanted to read the data in this contract using the getNum function. First, we'd have to define an interface of the lucky number contract. Notice that this looks like defining a contract with a few differences. For one, we're only declaring the functions we want to interact with, in this case getNum. And we don't mention any of the other functions or state variables. So it's also not passing anything, we're just declaring. Secondly, we're not defining the function's bodies. Instead of curly braces, we're simply ending the function declaration with a semicolon. So it kind of looks like a contract skeleton. This is how the compiler knows it's an interface. Contract skeleton. By including this interface in our dApps code, our contract knows what the other contract's functions look like. how to call them, and what sort of response to expect. We'll get into actually calling the other contracts functions in the next lesson, but for now let's declare our interface for the CryptoKitties contract. So I think this is similar to the way the header files work on C++, where you have one file where you put the functionality of things, and the other one you put the declaration of stuff. I think it works differently because it's on the blockchain, but the concept is the same. Put it to the test. We've looked up the CryptoKitties source code for you and found a function called getKitty that returns all the kitties data, including its genes, which is what our zombie game needs to farm a new zombie. The function looks like this. So there's the declaration, the arguments, kitty storage, kitty, and this is what the function does. Not get starting, just stating. The function looks a bit different than we're used to. You can see it returns a bunch of different values. If you're coming from a programming language like JavaScript, this is different. In Solidity, you can return more than one value from a function. Now that we know what this function looks like, we can use it to create an interface. Define an interface called Quiddity interface. So it's the same way. Yeah, contracts, then kitty interface. Remember, this looks like just create a new contract. Inside the interface, define the function getKitty, which should be a copy paste of the function above. Also, this isn't the function, the entire function. It's just but here, yeah, here's not passing the curly braces part, but so maybe it is the entire function, and I just have to copy this part. I don't understand why it's saying that it returns multiple values, but here there aren't return words, keywords. You find the function getKitty, which should be a copy paste of the function above, but with a semicolon after the returns statement, instead of everything inside the curly braces. Am I missing something? Where is the return statement? Inside the interface, define the function getKitty, but with a semicolon after the return. I always forget the semicolon. After the returns statement, instead of everything inside the curly braces. So I guess it's just, yeah. I guess these things are the return statements. And it's just not specifying here, but... Oh yeah, it's because you don't have to write return. Oh, now I get it. It says returns here in specifying what's gonna return, and then because you don't need to write return, is returning all these things. Now I think I understand. I forgot that it's different the way that it's written here. But I think I saw sometimes people writing return statements, so I'm not really sure when does it apply or when it doesn't. I think I will have to look into it later. And I think I'm gonna stop here. I think it's a good place to stop. And I'm probably, next time I come back, I'm probably gonna continue to do this and until I finish and then start to put space stuff. So see ya.